I'd like to look at some basic trigonometry notes today that kind of just get you through the actual ratios and some of the special right triangles that you're going to be dealing with. We'll save the trig on a unit circle and radians and angles greater than 90 degrees. We'll save that for another set of notes. But today let's get started just on some basics. First thing is the right triangles that they really love to use on both the ACT and the SAT are the 3, 4, 5. So 3, 4, 5 is the first triangle that's called a Pythagorean triple. And if you remember the Pythagorean theorem, which is, leg squared plus leg squared equals hypotenuse squared. And remember, the hypotenuse is always this long side that's across from the 90. It's always going to be over here by itself. And the two legs are going to be the two sides that make that 90. And the legs go over here on this side. Well, 3, 4, 5 is the first set of whole numbers that satisfies this formula. So 3 squared plus 4 squared does come out to be 5 squared. Most sets of 3 numbers won't satisfy that equation. Another one that you should probably be familiar with is his big brother. So if you multiply all 3 sides by 2, if you double them, scale it up, you're going to get 6, 8, 10. So oftentimes in the SAT, they're going to give you 2 of these numbers. You're going to need the third. And instead of solving the Pythagorean theorem, if you can kind of remember these combinations, it'll make things a lot faster. Another one that occurs a little bit less likely is if you triple this first triangle, then you're going to, if you triple 3, you're going to get 9, you're going to get 12, and you're going to get 15. So those are 3 sets that all kind of go together. So 3, 4, 5, 6, 8, 10, and 9, 12, 15. And of course, you could multiply by 4, by 5, and keep on going. The other one that they really like to use a lot is shaped a little bit differently, but it's a 5, 12, 13. So 5, 12, 13. And again, this satisfies the equation that 5 squared plus 12 squared equals 13 squared. So this is another set of 3 that is probably worth adding into your arsenal to save us some time. All right, let's kind of jump into some trig basics. So first thing is, when you have some sort of triangle, you have a ratio called sine, cosine, and tangent. And they're all kind of based on where your reference angle is or where you're standing. So let's just say that we have a triangle, and I'm just going to call it ABC. Well, the ratio of these sides, the ratio is just a fraction. Let's say that we are standing here. This is our point of view, or what's called our reference angle. Let's say we're standing on the angle A. Well, if I want to know, if I want to know what is the sine of angle A, and I want to know what that means, the sine of angle A is just the ratio of the side across, or the opposite leg, over the hypotenuse. All right, so if I'm standing here, opposite is this leg across from me, so this would be the opposite, and the hypotenuse is always across from the 90. So it's whatever those 2 numbers are. So if we go back and we just kind of use our little generic 3, 4, 5 triangle, the very first Pythagorean triple. So if I were to say, hey, what is the sine of angle A? Well, the sine of angle A would be the opposite leg over the hypotenuse. So it would be 4/5. And I don't know why that look more like a 6, so we're going to change it back to a 5. So 4/5. Right, so that's the opposite over the hypotenuse. Now, so that's the sine ratio, and oftentimes when you do the sine ratio, you kind of use a mnemonic device and you memorize it as SO, because you have S, O on top, H on bottom. So it's kind of a quick way to remember that sine is opposite over hypotenuse. Now let's look at the next trig ratio. The next ratio is the cosine. So again, I have my triangle, call it A, B, C. And if we want to know what is the cosine of angle A, and it's a ratio, it's a fraction, So here's my guy, here's my reference angle. So the cosine for A is defined as the adjacent or right next to leg over the hypotenuse. So if I go back to my little 3, 4, 5 triangle, and I call this 3, call this 4, call this 5, well, the cosine of angle A, the adjacent leg is not the far leg, not the one away from me. It's the one right next to me here. So it's this 3. And then the hypotenuse is still across from the 90, and it's still 5. So cosine would be 3 over 5. And oftentimes this mnemonic is named CAH. So cosine is adjacent over hypotenuse. That's where those 3 letters come from. The last one I want to kind of hit today is the tangent. So kind of going back one more time to our little 3, 4, 5. And we'll call this angle A. This is our reference angle. Well, the tangent is defined as the opposite leg over the adjacent leg. So there's no hypotenuse on this one. And this one is TOA, T-O-A, tangent, opposite, adjacent. So in this particular triangle, the tangent of angle A is the opposite leg. So remember, opposite is across from me, over the adjacent leg, the one right next to me. So the tangent of A would be 3 over 4. Okay? So that's the basic SOH CAH TOA. So when you put all that together, you have your sine, you have your cosine, and you have your tangent. And together, kind of sounds like a summer camp, but together that's what you learn back in geometry or maybe algebra 2 or maybe even algebra 1. But those are the basic 3 trig ratios. Now, one thing that the SAT really loves, so this is kind of a hack or a little trick that's super important, is when you have a right triangle, and let's just, do our little, I'm just actually going to make up a couple angles here. And let's just say that this angle is 30 degrees and this angle is 60 degrees. All right, so I have special right triangle here. I have a 30, 60, 90. I don't really like that 3, so I'm going to go in here and clean this up a little bit. All right, so a 30, 60, 90. So realize that, let's say that you're standing on, well, and actually before I even get into the numbers, let me kind of back up a little bit. Let's just go to a triangle. And let's just label him. I'm going to label him A, B, C. And then I'm going to label the sides. So since this side down here at the bottom is across from capital A, I'm going to call it little a. So that's side little a. The hypotenuse, we're going to call side little b. And this side, we're going to call side little c. If I were to say, hey, what is the sine of angle C? Well, angle C would be my reference point. So here's where my guy is. The sine of C is opposite over hypotenuse. So when I look across, this would be C over B, all right? Opposite over hypotenuse. And if I wanted to know what, let's say, the cosine of angle A is, all right? So if I kind of change position here, and now my guy is no longer, he's no longer there. This is getting kind of messy here. Sorry about this. But now if I say what's the cosine of A, and I put my person on A, I get my labels back on here, little c, little b, little a. Well, the cosine when standing on A is defined as the adjacent over hypotenuse, which is going to be also c over b. So you kind of come up with this fundamental idea that you get the same exact ratio or the same answer when you take the sine of one angle and the cosine of the other angle, and those two angles add up to 90 degrees, all right? And those are called complements to each other. If you recall from geometry, two angles are complements if they add up to 90 degrees. So kind of the gist of that, using some real numbers. So let me kind of go back here to my 3, 4, 5 triangle. And we put some angles. We call it ABC. So the big thing that I want you to understand is no matter where you stand, you know, if you want to do the cosine, let's say, of angle C, which is adjacent over hypotenuse, it's going to be the exact same answer as the sine when you're standing on the other angle, because the sine of A is opposite over hypotenuse. Now I want to kind of verify this with a graphing calculator just to kind of prove it to you. So let's look at a few angles that we know are complements. So for instance, let's look at the sine of 30 degrees, and then I want to compare that to the cosine of his complement, which would be 60, because they add up to 90. And maybe I'll do a couple more. I'll do the sine of, I don't know, 19 degrees, and then we'll do the cosine of 90 take away 19. 90 take away 19, that's how you find his complement. Well, that would be 71. And maybe one more. Maybe we'll do the sine of, I don't know, 68. And then we're going to compare that to the cosine of 90 minus 68, aka 22 degrees. All right, so let's just check these out on a graphing calculator, and let me kind of prove this concept to you. So we turn it on, we're going to clear it out. So when I do sine of 30, I get 0.5, all right? And when I do the cosine of 60, 0.5. So you're going to realize they're equal to each other. Let's try the other pair. Sine of 19 equals versus cosine of 71 equals. You'll see the exact same number over there. Same setup. And then last one, hopefully you believe me by now, but sine of 68, 0.927, cos of his complement, 0.927. So in general, something you want to understand is that the sine of x is always going to be equal to the cosine of 90 take away that value. All right? Or vice versa. The cosine of x is always going to be equal to the sine of 90 minus that number. This is the complement theorem that you need to know when you're doing the SAT. They seem to love this question. This is a very popular trig question, so you're definitely going to want to know it. Hopefully this sets you up to where you can solve some of the basic trigonometry questions that you're going to come across on the SAT.